The next thing that I want to go ahead and do as we're taking a look here in section 3.3 and introducing ourselves to the concept of vectors, not victors, is spend a little bit of time talking about this idea of vectors being equivalent and how we can actually show that. And the reason why I'm going to spend some time with this example is because it's also going to give us a way to talk about the magnitude for a specific vector as well, how it's found. It's all well and good that the text says that you use the distance formula, but it would be actually kind of nice to see what that looks like. So in this specific case, we're going to go ahead and determine if the following two vectors are equivalent to one another, meaning do they have the same direction and do they have the same magnitude. One of those tasks is going to be a little bit easier than the other. If we're interested in determining if these two have the same direction, one way to talk about that, since they're both directed line segments, is to talk about the individual slope of each one of these line segments. If they have the same slope, that's the same as saying they have the same direction. So here I'm going to make sure to note my different points. R and S forming the vector V are 1, 2, and 4, 4. P and Q forming the vector U are 0, 0, and 3, 2. Let's pop over to the notepad here for a moment. So to talk about their individual slopes, when we're talking about the slope for RS, we had R is the point 1, 2, and we had S is the point 4, 4. So slope, remember, is a difference in y's over a difference in x's. So we'll do in the top 4 minus 2, and in the denominator 4 minus 1. I'm taking the y coordinates of the second and subtracting the y coordinate of the first, then taking the x coordinate of the second, subtracting the x coordinate of the first. So this will give me 2 over 3. Now we'll look at the vector PQ. I guess it's more accurate to call it a vector U and vector V because they're directed line segments, RS and PQ. But either way, these ones had 0, 0 and 3, 2 as their points. So again, we're going to go ahead and find slope as a difference in y's. This time I'm going to take the first y coordinate and subtract the second y coordinate, the first x coordinate, and subtract the second x coordinate. The idea behind slope is that you can do it in either way so long as you maintain consistency. First minus second, first minus second. Y's on top, x is on bottom. If we do this, we end up with negative 2 over negative 3, removing a factor of negative 1. This becomes 2/3. So we've determined that they have the same direction. Now the question is, do they have the same magnitude? And this is where what they call the distance formula comes into play. But again, I'm going to talk about it a little bit more in the context of a right triangle. If we think about the endpoints for R and S that we had, R was at 1, 2, S was at 4, 4. Our magnitude is specifically the length of this directed line segment. And we're going to find that by forming a right triangle here, where we can find the lengths of the two legs by measuring the change in x values. This has a length of 3. And our change in y values, this has a length of 2. And we're essentially trying to find our hypotenuse here. So this is going to be 3 squared plus 2 squared equals our magnitude squared. So I'm going to write this out in its preferred form. This is RS. Oops. Got PQ on the brain. RS. But this is its magnitude squared, keep in mind. So this is going to be 9 plus 4 equals our magnitude of RS squared. When we take the square root of both sides, since we're talking about magnitude, we're not actually ending up with a negative value here. We're looking at the principal root of 13. And that's going to be the best we can do. Since 13 has no perfect square factors, that ends up being our magnitude. Now remember, our goal is not just to find magnitude, though this is a good thing to practice. We're checking to see, does PQ have the same magnitude? Well, in this case, with a little bit of replacement here, just replace these 2 points with the points for P and Q, we can see that yes, in fact, they have the exact same lengths of the legs, so the length of the hypotenuse here is going to be the same as well. The magnitude for the directed line segment PQ is also the square root of 13. So they have the same direction, and now we've determined that they have the same magnitude. As a result, we say that these two are equivalent to one another. Now, I don't know if this textbook has used this symbol or not, but the general symbol that we use for denoting equivalence in lots of areas is 3 lines. These two have both the same direction and the same magnitude, so we say that they are equivalent using this symbol between them. We wouldn't necessarily say they're equal because they don't have the same initial and terminal point, but because they have the same direction and same magnitude, it does mean that they are going to be equivalent to one another. Okay, so this was a short little example meant to kind of demonstrate, 1, how we actually find the magnitude for directed line segments, and 2, how we show that 2 different directed line segments or vectors are equivalent to one another. I'll meet you guys in the next part to kind of close things out for this section.